in problem 12.47, we have a ball resting on an incline, okay? And the only thing that's keeping that ball from rolling down is the friction force at this point right here and a horizontal force F, okay? And what we're asked to find is, what is that horizontal force? Uh, Given that this ball here has a mass of m and it has a force of gravity. Actually, this ought to probably be mg. That it has a radius r and an angle theta. That's the theta of the incline. What is that force? What's that unknown force? Okay. Of course, this thing is in static equilibrium, which in this case, we only need to be concerned with the sum of the torques, and the sum of the torques must be equal to 0. So what we have to do is sum those torques, set them equal to 0, and then solve for any unknowns that will simplify this down to a function of the angle. Now, if you look at the forces, here is this force here. I'm sorry, there's a force F applied here at a radius R from this point right here. This is the point about which we're going to sum the torques. So that the torque produced by this force, okay, is R, capital R, okay, the cross product between that and F, and the angle between R and F is this angle gamma right here, okay? So that torque would be the magnitude of R, the magnitude of F, times the sine of the angle between those two, and that's gamma. Now I have to add to that the torque produced by the force of gravity, and that'll be R, the little r right here, crossed into FG, okay, and then the angle between R and FG, I'm going to write as 2 beta, that angle right there. So I'm going to subtract off R crossed FG, and when I do that, I get the magnitude of R, the magnitude of FG times the sine of the angle between them, which is 2 beta. Really, this problem comes down to using the geometry to reduce basically down to the fact that we have one function, trigonometric functions that involve only the angle theta and or theta over 2. Okay, I've broken this picture up into triangles where this total angle from here to here is broken up into 2 identical triangles, each which has an apex angle of theta over 2. This is the vector r, okay, and here's the vector little r, and there's a series of triangles in here and reflex angles that will help us find the relationship between basically beta and theta and alpha and theta, where alpha is this little angle up here, okay, that I can use to analyze this triangle down in here to get the trigonometric relationships. Let's start out with trying to get everything into to one angle. And so what I can do is notice that if I look at this little triangle in here, alpha and beta are the 2 angles in a right triangle, and so alpha plus beta must be 90 degrees. Now I get the betas because these are reflex angles right here, okay? All right, therefore 2 beta plus 2 alpha must be equal to 180 degrees. This allows me to take this sine of 2 beta, okay, and write it as sine of 2 alpha. So I can get this expression in terms of alpha, okay? I'm going to try to get this expression over here in terms of alpha also. Now, if we look at if we look at gamma here, okay, you can see that gamma, okay, is equal to alpha plus 90 degrees, okay? So gamma equals alpha plus 90 degrees. So the sine of gamma is equal to cosine of alpha. So when I plug for alpha and beta here, if I substitute those in, then R times F sine of gamma is cosine alpha, okay, equals R times F sine of 2 alpha. I've already got that in, so I'm ready to start simplifying some more. I've replaced the sine 2 beta with the sine 2 alpha. So everything now is in terms of alpha. I have one more triangle here, and this is this little triangle in here where this side of this little triangle here is R over 2, and this side right here is R, okay? So I can get R over 2 is equal to the hypotenuse here, R, times the cosine of alpha. So R over 2 equals R cosine alpha. Okay, so I can come up here and see this R right here? I'm going to put R cosine alpha in there for it. So F times 2R cosine alpha, that's what capital R is, that equals R FG sine 2 alpha. So I can solve this now, F, in terms of alpha by just solving this algebraically. But it'd be nice to get the answer in terms of theta. So we have to go back to our triangles again and see if we can get alpha in terms of beta. We've already been through the fact that alpha plus beta, which are the two angles of a right triangle, must add together to produce 90 degrees. So we've been through this right here. Okay, but if you look at this big triangle here, this big triangle here, you can see that theta over 2 plus beta must be equal to 90 degrees. Okay, they're the two angles of a right triangle. So theta over 2 plus beta equals 90 degrees. Well, you can look at this and see, therefore, alpha must be equal to theta over 2. So you can replace alpha with theta over 2, and so that makes this just theta because 2 times theta over 2 is just theta, and then 2 cosine square theta over 2. Now, you could leave it at this, but remember that using the half angle formulas, the sine of theta is equal to 2 of sine theta over 2 times cosine theta over 2. So if you plug that in here, then the one of the cosines cancel and leaves you with it'll leave you with a sine over a cosine, which is the tangent of theta over 2. So here is the final expression that you're looking for right here, where mg is fg.